Okay, so good afternoon, everyone. So today we will discuss about the multi-temporal InSAR techniques. So I hope you have already attended the classes related to the principles of the InSAR and the D-InSAR. So here we will discuss the multi-temporal InSAR techniques. So before going into the detail, first we should understand the basic terms related to the multi-temporal InSAR techniques. So the first thing is the coherent signals. So whatever the InSAR techniques we are going to apply, so in all the techniques basically the signals should be coherent in nature. Coherent means, as you know, for generating one single interprogram at least two images are required. So you can say the phase difference of two signals is basically called the interferometric phase, and the graph of the phase difference is called the interferogram. So in that interprogram two signals are involved and both the signals should be coherent in nature. If they are not coherent in nature, it means you cannot generate the interprogram, or if you are generating interprogram, so that is not making any sense because a lot of noise will be there. So coherent means the signals of the similar characteristics, like the wavelength of both the signals should be same and the amplitude should be same. Okay, so these things should be similar, or both the signals should be sinusoidal or the cosine signals. So if such conditions are matched or meeting, then the signals are called the coherent signals. If you cannot say like one signal is L band signal, another one is X band signal, and if you are combining both of them, or you are calculating the phase difference of both the signals and generating the interprogram, so that is not possible. So point is both the signals of the single interprogram which we are going to generate should be coherent in nature, or you can say coherent term is coming from the coefficient of correlation. So you can say coefficient of correlation, or you can say the correlation. Okay, so if correlation is very high, it means correlation is related to the two variables. So you can say if one variable is increasing in one direction, another one is also increasing, so that we can say both the variables are correlated, or you can say the correlation between both the variables is positive. So if both of them are correlated, it means correlation coefficient of correlation is very high. So similar to this one, if both the signals are of the same characteristics, then you can say the signals are correlated or coherent. So the value of the coherence is varying between 0 and 1. So if coherence value is 0, it means the signals are not correlated, and the coherence value is very close to 1, it means the signals are highly correlated. So the intermediate values we can also decide. Let us say if the coherence value is less than 0.25, then you can say very low correlated signals, or from 0.25 to 0.75, then you can say the moderately coherent signals, or if the coherence value is between 0.75 to 1, then you can say the highly correlated signals. Okay, so this coherence level is very important when we are discussing about the InSAR techniques. So in these coherent signals, actually here two types of the points are mentioned here. You can see this is one type of the resolution cell, this is another category, this is another category. So here you can say in this resolution cell different backscattering information is coming. So few are shown by the blue lines, blue dotted lines, and one is shown by the solid red line. So this shows basically in this resolution cell so many types of the scatterers are there, and or you can say two category of the scatterers are there. So one scatterer is responding the backscatter energy very strongly. So you can say the backscatter information corresponding to this red response is very high, and the backscatter from the other targets represented by the blue colors is not that much high, or you can say the moderate level of the backscattering is happening from the other types of the targets. Okay, so you can say within this resolution cell two types of the scatterers are there. One category of scatterers are responding moderately, and another category of scatterers is responding very strongly. Okay, So such kind of the pixels, or you can say the resolution cells, are called the persistent scatterers. Point is, whatever the red color response is there, it means there is a very strong target which is responding in all the signals. Means suppose if one image is acquired at time t1, another image is acquired at time t2, t3 and so on. So in all the images this particular target is responding very strongly. So that's what the similarity between the signal is maintained throughout the investigation period, and hence these types of the targets or the resolution cells or the pixels are called the coherent scatterers. Same time you can see on the other side, in this particular resolution cell all these scatterers are of the same type, or you can just same type of the scatterers are there, but the response from all the scatterers is not very strong, or you can say that is of the moderate scale. So you can say the coherence level, if we acquire such images at time t1, t2, t3, and then we try to calculate the coherence or correlation between t1 to t2, t2 to t3 like that, then the coherence level is not very strong, that is a moderate coherence. And in this case if you calculate, then the coherence value will be very high. So that's what it is called, the coherent signal. But this is persistent coherent, and this is also coherent but moderately coherent signals, and these are also called the distributed scatterers. Okay, and similar examples is like this. In this particular resolution cell, two types of the targets are there. One is blue, another type of the targets are there which are responding the backscatter energy by the green color. So you can say two types of the scatters are there, but both the categories is responding more or less in the similar manner. So again the coherence is not very high, or the coherence is of the moderate scale. So these types of the resolution cell again called as a distributed scatterer. So here I have mentioned two type of the scatterers. One is persistent scatterer, another one is distributed, another one is another category of the distributed scatterers. So same way you can assume the other types of the resolution cell where moderate level of coherence you are getting. So those resolution cell or the pixels are also called the distributed scatterers. And the other type of the resolution cell you can also assume where you are not getting very high coherence level or moderate scale coherence, but you are getting very low coherence level over those resolution cells. So those resolution cells are basically called the noisy pixels. So in the multi-temporal InSAR techniques, we will only consider either persistent scatterers or the distributed scatterers. We are not going to consider those noisy pixels at all. Okay, so you can say now persistent scatter, in short we call it the PS, and distributed scatters we call it as a DS. So you can say in multi-temporal InSAR techniques only PS and DS pixels are considered for the InSAR applications. Other pixels we are going to ignore. Okay. Then second parameter is the phase stability. Means phase stability is also very important. If phase is not stable, or you can say phase is fluctuating very rapidly, it shows basically the signals over that particular area are not stable, or they are basically getting affected by so much of the noise, or you can say signals are becoming decorrelated. Okay, so if phase is not stable, like if suppose some natural environment is there, let us say in the hilly region, some rainfall is happening, or the forest patches are there, and some wind is also blowing. So the structure of the trees are also going one position to another position like that. So in during that particular time, if signal is captured or image is captured, it means the phase will not be stable. So that is basically instability situation. So unstable phase is not suitable for the interferometry, especially for the multi-temporal InSAR techniques. Then question is that is fine, but how to select these types of the features, means these types of the PS or the DS. So there are number of criteria. by which we can select these types of the pixels from the entire image. In the image thousands or lakhs of the pixels are there, but we are not interested in all those pixels. We are only interested in the PS or the DS. So thing is, from millions of the pixels, how we can pick these PS and DS, which are limited in number. Okay, so number of criteria are there. So first on the basic criteria is, that is basically called the amplitude dispersion. So what we are doing basically here in SAR images, we have the amplitude images as well as the phase images. So we are calculating the amplitude dispersion, that is nothing but the standard deviation of the amplitude divided by the mean amplitude. So amplitude values are there over each and every pixel. So we since so many pixels are there, so statistical parameters we can calculate easily. So first we will calculate the standard deviation of that particular image, and then mean of the amplitude values, and then we will divide standard deviation by the mean of the amplitude. So whatever we are getting, that is called the amplitude dispersion. So this quantity should be as small as possible. If suppose the dispersion is very large, it means the signals are getting decorrelated. It means if this amplitude dispersion value is very large, it means those pixels are not satisfying the criteria for the PS and DS. So again you can put certain threshold over the amplitude dispersion, so that you can identify, okay, if amplitude dispersion is below this particular value, then those pixels can be considered as a PS or the DS. Okay, and if dispersion value, amplitude dispersion value is more than that threshold value, it means those pixels are neither PS nor DS. So that particular value, threshold value, is around 0.4. So you can say if amplitude dispersion is less than 0.4, we can consider the point as a PS and DS. If it is more than 0.4, then it is not PS or the DS. So this is the basic criterion for selecting these PS and DS, or these PS and DS are also called the measurement points. Okay, so you can say MPs or PS or DS. So these things we can consider, or by applying this particular criteria. And then second thing, fourth thing is the interferometric phase. So this we have already shown somewhere. Suppose you want to generate the interferogram, it means you have to have the two signals of the similar characteristics, or you can say two coherent signals you should have. And if you see the electromagnetic radiation, so it has electric field, magnetic field, and direction of propagation. So magnetic field we are not considering, as I have already mentioned in the first class. So we are only focusing on the electric field vector. So electric field vector is associated with each signal of the interferogram. So suppose EA is the electric field vector of signal A, and EB is the electric field vector of signal B, or you can say the second signal. So this signal is a complex in nature, this signal is also complex in nature. So that's why this dagger is mentioned. It means this is the first signal into complex conjugate of the second signal. Okay, so this electric field vector can be written as a amplitude like EA equal to EA0 e to the power I phi A, and EB can be written as a EB0 e to the power I phi B. Okay, so you can say that is complex in nature. So amplitude of both the signals are getting multiplied, but the exponential part is associated with both the signals, but they are not getting multiplied, they will getting subtracted. Okay, so here you can say this is called the resultant amplitude of the electric field vector, or you can say if you are combining two signals in this particular manner, then this particular manner is called the interference. Okay, or you can say the superpositions of the signals. So in this situation, the amplitude of both the signals are getting multiplied, but the phase of both the signals are getting subtracted. Okay, so this phase difference, which is we are getting phi B minus phi A. Phi B means phase of second signal, minus phi A means phase of first signal. So this is nothing but the simple phase difference of both the signals. So this phi B minus phi A is called the interferometric phase. So this interferometric phase, or you can say this generally we can represent as a delta phi. So you can say delta phi equal to phi B minus phi A, that is interferometric phase, and the graph of this one is called the interferogram. and this is the expression for the coherence. So the coherence, here we are representing by term gamma, and with dual suffix m and s. M stand for master here and s for the slab. So you can say master slab, or you can say the coherence between master and the slab images. So it is just this equation is similar to the coefficient of correlation. So you can say the expected value of master into complex conjugate of the slab divided by square root of expected value of Zm whole mod of square and expected value of Zs mod of square. So if we solve this, then it is again a complex quantity. So this is basically mod of gamma ms is called the amplitude of this coherence, and e to the power I phi is called the exponential term, and phi is called the interferometric phase. So this phi is nothing but phi b minus phi a. So this way basically we can calculate the coherence, or you can say the correlation between the signals. So these are the basic terms. If you understand these terms, then you can understand the multi-temporal InSAR techniques easily. And then another question is, suppose for a single interprogram 2 images are required. So out of these 2 images, one image is considered as a master, or you can say the reference image, and the remaining image is called the secondary image, or you can say the slab image. Earlier people were using the term master and slab. Now people are not using the term master and slab. They are using, everybody is using reference and the secondary image, or you can say primary and the secondary image. Primary means master, or you can say the reference image, and the secondary means the remaining image, or the second image is called the secondary image. So point is, if suppose 2 images are given to you, then how to select which one is reference image and which one is secondary image. So you can say the selection of reference image is also not very simple. It is basically based on some calculation, and that calculation is we have to calculate basically the coherence level, and if coherence is high, okay, suppose I am giving you the 3 images. So out of 3 you have to choose one image as a reference, and the remaining 2 images will be secondary images. Then you have to make the pairs. Suppose first image you are considering as a reference image, then second and third will be the secondary images. So you will form the pairs like between first and second and first and third, because the reference image will be common. So you will see the coherence between first and second and first and third. If you add both of them, then the whatever the coherence is coming, that should be maximum. Maximum in the sense, suppose out of 3 images, in first trial you are considering first image as a reference image and others are secondary, and you are making pairs between first and second, first and third, and you are calculating the coherence of both the pairs, and you are adding both of them. Okay. In second situation, what you are doing, you are considering second image as a reference, then you are making pairs between second and first, second and third, then again you are having the 2 pairs, and for each pair you are calculating the coherence, and again you are adding. So some numerical value you are getting, means in first situation you are getting some sum of 2 pairs, and in now second situation also you are getting sum of 2 coherence of 2 pairs. And the third situation may be like, if you are considering the third image as a reference, then again you are making the pairs between third and second, third and first. So third and second 1 pair, third and first another pair. So if you are calculating the coherence for both the pairs and you are adding both of them, then now there are 3 situations now. Okay, first image as a reference, then you are calculating coherence and adding both the sum of coherence of both the pairs. Then in case of second and the third, then out of these 3 you will choose in which situation the maximum coherence is there. So suppose in case of third image, where you are considering third image as a reference, and then you have calculated the total coherence. So that coherence is highest, or you can say highest among all the 3. Then the third image, you can say the third image can be considered as a reference image. The first and second you cannot consider, because the sum of coherence in case of first and second combination is not maximum. So point is, if you have 100 images, so you have to basically choose or do the calculation one by one. Means in first trial you have to keep first image as a reference, and then make so many pairs and calculate the coherence for all the pairs and add all the coherences. Then in second step you consider a second image as a reference, and then others will be secondary images, and now make the pairs and calculate the coherence for each pair and add all the coherences. Okay, then in third trial keep the third image as a reference, make the pairs, calculate the coherence for each pair, then add all the coherences. So by this way 99 pairs you will calculate. Okay, then you will compare, okay, in which combination the maximum coherence is there. So corresponding to that particular image you can consider as a reference image. Okay, so what is the formula? This calculation you are not doing. Suppose 100 images are given to you. If you are doing manually everything, then it will take lot of time. Okay, so manually it is not possible. So everything is done in the computer systems. So computer, some programs we are making, and using that program the coherence values are calculated very easily. Okay, so what is that formula? That formula is given here. Here you can say gamma r. It means this is the coherence for a reference r, equal to 1 upon s. S is the number of secondary images. Suppose 100 images are there. So out of 100, 1 image is reference. So 99 are secondary images. So here you can say summation of means sum of all the coherences, where s is starting from 0 to s. So and these three brackets are there. The first bracket tells us 1 minus b perpendicular sr, means this is the perpendicular baseline between secondary and the reference image, divided by bc, that is again the perpendicular baseline, but that is the critical value of perpendicular baseline. Okay, this is the spatial baseline. This spatial baseline is nothing but the physical separation between the satellites, or you can say first image was acquired from this low satellite position, another image, second image was acquired from this satellite position, both the images of the same pair. Okay, so the physical separation between these two satellites is called the baseline. And if I am drawing, suppose this trajectory is like this, means this is circular trajectory. So one trajectory is shown here, another may be looking somewhere here, means some height gap is there. So if you draw a perpendicular from the lowest one to the highest one, because this is the highest position, so from here to here if you draw a line, and from here to here you draw a line, so then you draw a perpendicular from here to here. So the distance or the length of this perpendicular line is called the perpendicular baseline. Okay, so point is, if this gap, satellite position, orbital gap, if it gap is more, it means the coherence between the signal getting reduced. Or you can say, if both the signals are taken from the same satellite position, so you can say spatial baseline or perpendicular baseline is 0, and the signals are highly correlated. As the distance increases, the baseline increases, and hence the coherence value decreases, and you can say up to as the distance is increasing, the coherence value is going to decrease. But if it is increasing beyond a particular value, then both the signals are completely decorrelated, means there is no coherence between the signals, and that particular value is called the critical baseline. So you can say this BC is the critical perpendicular baseline. If baseline, or you can say the separation between the satellites, is more than this particular value, then the signals are completely decorrelated, and that pair of the images is not suitable for the interferometry. Okay, and this actual perpendicular baseline is always smaller than the critical baseline, or you can say the numerator is basically the actual baseline, that is much smaller than the critical baseline. So basically if you are calculating this, it means you should know the perpendicular baseline of that particular satellite and that particular pair. Okay, so the critical baseline is fixed for satellite. Suppose you are talking about the RISAT one, it means critical baseline is fixed. Similarly for the Sentinel one, RadarSat, NVSat, for every satellite this BC is different. Okay, so perpendicular baseline should be much smaller than BC. And suppose in a typical case this particular value is equal to BC, so this divided by this will be 1, so 1 minus 1 will be 0. So the overall coherence will be 0. Doesn't matter what is the value of this factor or what is the value of this particular factor. Okay. So point is the actual perpendicular baseline is always less than critical baseline, and the same thing and same term is like is here 1 minus TSR upon TC. TSR means temporal baseline between secondary and the reference image, and TC is the critical temporal baseline. Temporal baseline is what? That is basically, suppose in one interferogram 2 images are required. So one image was acquired at time t1, another image was acquired at time t2. So the time gap between both the images is called the temporal baseline. So suppose first image was acquired on 1st January, second image was acquired on 12th January. So first 12th minus first, any 11 days. So 11 days is basically the temporal baseline. In fact, that is 12 days we consider generally. So you can say 12 days is the temporal baseline. So again this time is increasing. Suppose first image is 1st January, second image is 28th February. It means time gap is increasing. And let us say first image is 1st January 2015, another image second image is 14th July 2025. It means 10 years gap is there. So if more temporal gap is there between the images, it means they are not correlated, or you can say coherence becomes very less, or you can say the signals are completely decorrelated, or you can say as the time difference between both the images increases, the coherence level decreases, and if this time is beyond a particular value, then these signals are completely decorrelated. So that particular value within which some correlation is there, so that critical value is called the critical temporal baseline. So again in the same manner, actual temporal baseline is always less than the critical temporal baseline. Okay. So this is also given for each and every pair. Suppose you know the acquisition time for each and every image. So whatever the pair you are making, so you know the time gap. So the time gap is nothing but the temporal baseline, and the critical temporal baseline is also fixed for each and every satellite, or even the for the target, different types of the targets. And the third term is called the 1 minus, this is also similar factor, 1 minus FDC between SNR, between secondary and reference, divided by FC. FD is called basically the Doppler baseline, and FC is the critical Doppler baseline. So Doppler baseline is basically the Doppler effect. Doppler effect is because of the motion of the satellite. So suppose satellite is acquiring the data and some swath is there. So swath is, let us say, 400 kilometer or 250 kilometers, something like that. So and the satellite is moving in the along the satellite trajectory or along the azimuth. So what is happening? This whole coverage or whole scene coverage is having its central frequency. So that is called the Doppler frequency, and the forward direction means the this side of the scene and the backward side of the scene. So signals are coming from the forward side of the scene also, and signals are also coming from the backward side of the scene, and satellite itself is moving towards this side. So what is happening? The signal which is coming from this side, that is appears like it is moving towards the satellite, and the signal which is coming from the back side, that appears like that side is going away from the satellite. So this particular thing is called the some frequency shift you are getting, because the relative speed of the forward side is more and the relative speed of the backward side is less. So because of this mutual speed, the some frequency is changing. So that difference in frequency is called the Doppler frequency shift, or you can say Doppler shift. So that central frequency, it doesn't mean that the coverage of that scene you are increasing manifold. That is not possible. Okay, if you are the size you are increasing manifold, it means the signals or the Doppler shift is very large. In that case, the signals are not correlated and not useful for the interferometry. So the scene size is up to a certain extent. So within, or you can say the maximum size of the scene where we are getting the correlated signals, so that maximum size is called the critical Doppler frequency, and the actual one is basically less than the maximum size of the scene. So depending upon the strip map or the ScanSAR or other acquisition modes, so the actual scene size is much less than the critical value of the Doppler frequency. So these three factors are important, and for each pairs these factors will be given, and you have to just calculate the product of all these three factors and sum of all these factors, and then you will calculate the gamma. Okay, so wherever you are getting the maximum gamma, that is called the maximum coherence, and corresponding to that image you have to consider as a reference image. So this is SAR interferometry basic principle. Suppose this is the actual terrain on the Earth surface. This is some datum. So the actual terrain height is, let us say, small h, and one satellite acquisition is taken from this satellite position. So one image is acquired from this position. Another image was acquired from this position. So these two SAR acquisitions are there. So this gap is called the B baseline or spatial baseline, and if you draw the perpendicular, so this is perpendicular distance, or you can say the perpendicular baseline, and this is called the look angle. Okay, so using because these are the radar devices, so they are capable to calculate this range, because radar stands for radio detection and ranging. So this distance they can calculate. Similarly, this distance can be calculated from the another scene, and this look angle for this one and look angle for this one is also known. So using the trigonometry, we can calculate very easily this height parameter. Okay, so this height parameter is nothing but the topography of the Earth surface. So you can say the topography can be mapped using two SAR images, or you can say by generating an interferogram, or you can say by calculating the phase difference of both the signals, the height can be calculated. Okay, so you can say height means the popular application is the DM generations. So SAR based DM generation is also possible. So you can say this is the SAR application for the topographic mapping. Okay, here you can see the live examples, like two satellites are acquiring the same images, and if you are combining both of them or superimposing both the signals, then the actual topography you can generate, or you can say the DM can be generated by these two SAR images. So this is the basic principle of the SAR interferometry. It means two complex signals are combined together and the phase difference is calculated. That phase difference is converted into path difference, because very famous formula is there. Phase difference equal to 2 pi upon lambda into path difference. So phase difference from these two signals is coming. 2 pi is constant, lambda is the wavelength of this radiation which is we are using in the microwave portion, and path difference you can calculate. So the path difference may be in the horizontal direction or in the vertical direction or any other inclined direction. So this actual topography or topographic height, or you can say the elevation, is the vertical distance. So this vertical distance is nothing but the path difference. Okay, so from the phase difference of these two images, path difference, or you can say the topography, can be calculated very easily. So this is the basic principle of the SAR interferometry. But if you see the mathematically, so I can just tell you, especially for the deformation analysis, how the deformations we are going to calculate. So here you can see in this particular example, let us say first see this equation, because this is the Maxwell equation, wave equation, and everything is derived from this equation itself. So it is very much important. But if you see the expression for the electric field vector, this we have already seen in the so many lectures. So electric field vector equal to amplitude into e to the power I into phase. That phase can also be written as a sum of the multiple factors like k dot r minus omega t plus phi. So k dot r is the propagation phase, or you can say geometric phase. This is the temporal phase. This is the scattering phase. Okay, so now in this particular course we are interested in this factor, or you can say these phase factors. Okay, so what we will do now, we will write the phase of both the signals. Suppose in one interferogram two signals are there, so we will write the phase difference phase of both the signals, then we will subtract them and then we will see what we can get from the subtraction of these two signals. Okay, so suppose this analysis we are doing at a particular time, let us say time is 0, so omega t will be 0, so only these two terms will be there, k dot r plus phi. Phi is the scattering phase, k dot r is the geometric phase. So in other terms we can write like this, this k dot r is a phi geometric and phi we can write, let's say, phi scattering. Okay, so this geometric phase plus scattering phase we are writing for both the signals. Let us say phi a, or you can say phase of the signal a equal to geometric phase of a plus scattering phase of a. Same thing, same way the phase of signal b equal to geometric phase of b plus scattering phase of b. Now this situation we are going to apply for the deformation analysis. So here you can see, suppose one target is there on the surface, that is P. So when no deformation is happening, that time the target was here itself and the image was acquired from satellite position A. So what is happening? This is radar, nothing else. So signal is going towards this target and coming back. So you can say the distance from here to here is r, then again from here to here is r. So the total travel distance is twice of r, or you can say 2r. So when no deformation was happened, our target was here itself, that time the image was acquired from this satellite position. Now by any reason some deformation has happened, then this target has moved from its original position to its new position, let us say P prime. Okay, so the distance from the P to P prime is small d. So small d is nothing but the displacement, or you can say the deformation. Okay, displacement, or you can say the path difference. So once the deformation happened, that time again the image was acquired from another satellite position, that is, let us say, satellite position B. So again from here the signal is going to P prime and then again coming back. So whatever the distance is, let us say small r distance is there, then it becomes 2 times small r. Okay, so this particular situation means so many triangles we can generate over here, like triangle from here to here, then here to here, and then this is one triangle, or from here to here means B to P, then P to P prime, then P prime to B. So this is another triangle, or triangle between A to B, B to P, P to A, another triangle, or triangle from A to B, B to P prime, P prime to A. So you just think here so many triangles are possible. So for a triangle, suppose one angle, two sides are known, then other things you can calculate, or you can say one side, two angles are known, then other sides and the angles of the triangle can be easily calculated. So point here is the distance from here to here it is known, the distance from here to here it is known, and the look angle means satellite is sending signal from here, so this angle, that is called the look angle. Okay, so look angle from this satellite position is known, similarly the look angle from this satellite position is known. Okay, so now point here is two angles are known and two sides of different triangles are known. And what happens, suppose this, and the baseline is also known, means the gap between this and this is also known. So you can say this side is known, this side is known, this angle is known. Okay, similarly if you draw this triangle, let us say B to P prime, P prime to P, P to B. So what is happening, this side is known, this side is not known, but that can be calculated from this particular triangle, because if you see this triangle A to B, B to P, so what is happening, A to B is known, A to P is known, so B to P we can calculate, and this particular angle is also known. So it means from this particular triangle BP can be calculated. Now in this particular triangle P to B, B to P prime, and P prime to P. So this triangle, now this side BP is known, B prime is known, it means two sides are known, and the third side can be calculated. Simple trigonometry. If you are using single trigonometry, then D can be calculated by this particular configuration. So same thing we are trying to understand from this mathematical formulation. So here you can see The same expression if you are combining two signals by this for by means of interferometry. So this is the phase difference. So now we are calculating the phase difference of this phi A and phi B. So here it is mentioned phi B minus phi A. So phi B is the sum of these two terms. This is also sum of two terms. So for instance, let us consider the scattering of both the signal is same. Let us say atmospheric conditions are same. So if we subtract phi B minus phi A, so the scattering component we are assuming same, so those will be cancelled out. Only the difference of geometric phase will be there. So phi B minus phi A means geometric phase of B minus geometric phase of A. So this phase difference is nothing but delta phi. Here I have added the term INT. INT stands for interferometry. So you can say interferometric phase is nothing but the geometric phase of signal B minus geometric phase of signal A. So if you see the geometric phase, this is phase difference. So geometric phase we can write phase equal to 2 pi upon lambda into path difference. So in this journey the total distance is twice. So in place of 2 pi upon lambda into path difference, we can write 4 pi upon lambda into path difference. Okay. So geometric phase of B, we are writing 4 pi upon lambda into BP prime, because this is the distance travelled, BP prime, minus geometric phase of A, that is again 4 pi upon lambda into AP, because this is distance travelled by the signal is AP. So that AP is mentioned here. Now we are just rearranging this equation. So BP is subtracted, BP is added. So by this way this equation becomes like this. So here you can say this particular term, green colors, BP prime minus BP. So here you can see BP prime and minus BP. It means in this particular triangle we are saying P prime P to B, then B to P prime in this triangle. Okay, BP prime minus BP, if you have, it means you are able to calculate small t. So this particular term is again the phase. You cannot say this is the phase path difference, but path difference is there, but overall it is equivalent to the phase. So this is called the basically the deformation phase. And this red colored term 4 pi upon lambda BP minus AP. So BP minus AP. So this is related to the DM phase, or you can say topographic phase. If you are calculating images from two different satellite positions of the same area, it means you are able to generate topography of that region. It means a similar situation is happening over here. BP minus AP means BP and AP means both the satellite positions are looking towards the single target without deformation. It means they will measure the topography of this particular region. So you can say this particular term is called the topographic phase, this is called the deformation phase, and now this is interferometric phase. So now from this equation we can say interferometric phase is equal to the sum of deformation phase and topographic phase. Okay. So this topographic phase you can calculate from known DM. Suppose you have the high resolution DEM, so it means the height you know. So from that height you can calculate the phase also. So this particular factor you can calculate from the DEM, and this phase difference you are calculating from the phase of through two signals. It means in this particular equation this is already known, which we have already calculated by subtracting the phases of two signals. This is the deformation phase which we need to calculate, and this we are simulating using the existing DM. It means this is known, only unknown thing is this one. So from this equation three things are there, two are known, one is unknown. So one can be calculated very easily, and which is nothing but the deformation phase, and from deformation phase deformation can be calculated, like deformation phase equal to 2 pi upon lambda into deformation. So here you can see from this expression we can also write like this, delta phi int minus this topographic phase, means delta phi int minus topographic phase equal to what will be left, this one, this is displacement phase, that is called phi displacement. So if we subtract the topographic phase from interferometric phase, then this difference is called the differential SAR or you can see a differential InSAR, because this is interferometric SAR. That's why this difference is denoted by another term delta phi dint. So delta phi is the phase difference because of the difference of these two terms. D stands for differential, int stands for the interferometry. So you can say differential interferometric phase equal to interferometric phase minus topographic phase, which is almost coming equal to the displacement phase, or you can say deformation phase. And this deformation phase you can calculate like 4 pi upon lambda, like phase difference equal to 4 pi upon lambda into path difference, and that path difference is nothing but this pp prime, or you can say displacement from p to p prime. So this phase displacement phase you can calculate from this relationship 4 pi upon lambda, lambda is known, 4 pi is constant, so this can be calculated. So by this way, means by combining the phases of the two signals or two SAR signals, we can calculate the deformation by this particular manner. Okay. So from these equations we understand the deformation or the interferometric phase is equal to the deformation phase plus topographic phase. But keep in mind, this particular equation we received after many assumptions. Many assumptions means initially we made omega t is equal to 0. So omega t term we ignored. Then in the next step we assumed okay the scattering phase of both the signal is same, that's what they have cancelled out. So that was another assumption. But in reality when we are acquiring one set SAR image, then another SAR image, in those situations the atmospheric conditions are totally different. So if atmospheric conditions are different, it means the scattering of both the signals will be different. So the scattering phase is not same way omega t we are assuming 0, but in reality it is something. Okay, suppose the time gap is t1 to t2, so some time gap is also there, so that you cannot ignore. So point is, after considering these assumptions, we are getting this simplified form of the interferometric phase, which is sum of displacement phase and the topographic phase. But if we are not ignoring those terms, then we will get something else also. Means interferometric phase is not only the sum of the displacement phase and the topographic phase, it is more than that. So what is more than that? That is basically shown in this particular equation. So now here you can see this interferometric phase is equal to the displacement phase, which is this one, plus topographic phase, which is this one, plus other terms you can see. This is phi SET, that is called solid earth tide phase, and this is the flat earth phase, this is atmospheric phase, this is orbital phase, this is some noise, and this is 2 pi n is the integer. So this n is calculation of n is also very difficult, and the calculation of n is also called the phase unwrapping term. Okay, so now you can see from this particular equation the difference interferometric phase is not only sum of displacement phase and the topographic phase, this is more than that. So what is more? That is solid earth tide phase is more, flat earth phase is there, atmospheric phase, orbital phase, noise, and unwrapping term. So now in this equation you can just understand this interferometric phase means the phase difference of two signal is affected by the displacement phase. Displacement phase means the motion of the targets on the surface. If motion is happening, it means that difference of two signals will be increased or decreased. Okay, or you can say interferometric phase will be affected by the motion of the targets, plus SET solid earth tides. Just like in the ocean you have different types of the tides. So tides are going up and down like this. So these tides are generating over the water surface, especially in the oceans. These are also visible in the rivers or some lakes or water bodies. So these my point here is the similar types of the tides are also observed over the land surface. Here whatever the land on the land we are living, that land is also going up and down, or you can say similar tide, means the tides similar to the ocean surface are also developing in the land surface. So that those tides are also basically contributing the difference between both the signals, or you can say in the interferometric phase. So we should understand how much tides are being developed over our study area. Okay, so continuously people are measuring those tides also. So those data sets you can use and you can understand, okay, this much tide is developed in this particular region, and hence this much contribution is there from the solid earth tide in the interferometric phase. Similarly, the topographic phase, because hilly regions and land is going beyond the geoid or the sporite, so that height is nothing but the topography. So because of the topography also some contribution in the phase difference is generated. Then flat earth phase, because we are assuming earth is flat, but it is not flat, this is spheroid. So when we project from the 3D, or you can say actual shape of the earth is like 3D, so if we change from the 3D to 2D, so this conversion is basically reflecting the flatness of flat curve, or you can say the curvature of the earth is generating some component in the phase difference, or you can say in the interferometric phase. So that phase component is called the flat earth phase. And then of course the atmospheric phase means atmospheric conditions are very difficult. The atmospheric compositions is changing from one position to another position, like over the Indian region or over the US or Europe. This atmospheric composition is totally different. So you can say spatially they are varying. Same way, temporally they are also varying. Suppose in the winter season composition is different, in the summer season composition is different, in the rainy season the composition of the atmosphere is different. Okay, so because of those compositions, especially on the temporal compositions, the signals are getting delayed. So you can say signal A is getting delayed in one way, signal B is delayed by another way or by another factor. So delaying factors are different. So because of that, some phase difference is generated in the both the signals. Then orbital phase, this is another phase component, like the satellite is transmitting the signals. So suppose the signal was transmitted from satellite position A, so that time the satellite position should be known very precisely. If you don't know the precise position of the satellite, it means you are not aware about the actual starting point of the transmitted signal. So if starting location is not known, means from where the signal has started, so because of that positional errors, some phase difference will be generated in the interferometry, and that is coming because of the Heisenberg uncertainty principle. Because if some body is in the motion, so if you are targeting the position and the momentum of the body, and if you want to monitor both the things simultaneously with great accuracy, it is not possible. So either you can measure the momentum very precisely, or you can measure the position very precisely. So satellite is moving continuously, so the location from where the signal was transmitted, that is not accurately known. So because of that uncertainty in the orbital positions, some phase difference between both the signals is generated, and that phase difference is called the orbital phase. Okay, so that is called the orbital phase, or you can say the orbital inaccuracies are also reflecting or contributing in the interferometric phase. Then this term is called the noise phase. So this noise is there. For example, as we have already seen the baseline concept. If baseline is more, the signals are decorrelating. If more and more baselines are there, or larger baselines are there, it means more decorrelation is there. It means coherence is less or decorrelation is more. It means decorrelation noises you are inviting. It means at the time of selection of the images for the interferometric applications, whatever the images you have acquired, so they are governed by certain baselines, temporal baselines, spatial baselines, and the Doppler baselines. and all the baselines are not 0. Some finite baselines are there. Since they are not 0, it means the signal is already decorrelating. It means that decorrelation noise is there for a given set of images, whatever you have chosen. Okay, so whatever you have taken means now you cannot further minimize the baselines. It means whatever the baseline has chosen, that baseline will remain there, and the decorrelation corresponding to that baseline will remain into the signals. So you can say that much noise is there in the calculations. So that is called the decorrelation noise. So that is represented by phi noise. But keep in mind the other components like SET, flat earth phase, atmospheric phase, orbital phase, these you can remove by applying corresponding data sets. But the phi noise you cannot remove. Whatever the noise you have invited at the time of data selection, that will remain till the end of this analysis. And 2 pi n, by means of phase unwrapping, you can calculate the value of n. 2 pi is already constant. So this equation is very important. So point is, if you are interested in the deformation analysis, it means you are interested in the phi displacement, and other phase components are not required for you, or you can say those components are unwanted, or you can say those phase components are non-deforming phase components. So these non-deforming phase components you have to remove, so that you can calculate precise displacement phase, and hence then you can calculate the precise displacement. Okay, so you can say the precise calculation of phi displacement is not very easy. Means you have to remove these contributions, and these contributions you cannot remove in a single step. You have to remove one by one. Let us say in one step you have removed the contribution of SET, then another step the topographic phase, another step flat earth, then atmospheric, orbital. By this way, means so many steps are required, and this way you have in this interferometric processing, so many steps are there, and this particular processing is called the InSAR processing chain. So keep in mind, this particular interest requires the optimal removal of the other component. At same time, you keep in mind the phi noise cannot be removed. It means the contribution of phi noise will always be there in the interferometric phase, and that you can consider as a displacement phase. So whatever the displacement or deformations you are calculating from the interferometry, in that the contribution of noise will always be there, but you have to quantify how much noise is there with the data set. Okay, so this is the one, and the application of displacement phase are many. Like you want to analyze land subsidence, or glacier melting, or dam tilting, or the bridge health monitoring, or the plate tectonic movement, or the landslides. These are all the examples of the phi displacement. Okay, so for this way the phi displacement is very important. Okay, now keep in mind, this deformation analysis is not only the application of the interferometry. So from this equation you can see phi topography is also there. It means if you want to generate the DEM from the interferometry, that is also possible. It means in that case our interest will be here, and in that case other components will be unwanted, like this and the other components are unwanted. So if you want to generate the DEM, so you have to remove other components very precisely. So what will be left after removal? What will be left? Only the contribution of the phi topography. And then phi topography you can use like this formula: phi topography equal to 2 pi or 4 pi upon lambda into height. So that height parameter you can calculate from the topographic phase. So you can say this is the another application of the InSAR or interferometry. Okay, another application may be like atmospheric modeling. So means how much signals are getting delayed in the atmosphere. It means for atmospheric applications this particular term is important, or you can say in that case your interest is here. It means you want to calculate the contribution of the phi ATM very precisely from the interferometry, and in that case other components are unwanted for you and you have to remove them one by one. Okay, so from this particular equation you can say there are so many applications of the interferometry. One is atmospheric modeling, another one is topographic mapping, another application is the deformation mapping or deformation analysis, and for deformation so many things we are considering simultaneously. So this way you can understand the potential of the SAR interferometry. Now this extended version of the same equation is written here: phi, flat earth, displacement, SCT, topographic, means what are the regions by which these components are contributing. So these things you can read later on, but I have already explained those. Okay, so here the InSAR technique, as I already mentioned, like phi displacement differential interferometry equal to interferometry minus topographic phase equal to displacement phase. Okay, it may be 2 pass or 3 and 4 pass InSAR techniques. So in this technique basically we are calculating the phase difference over each and every pixel in the image. That is the biggest drawback of this technique. As I mentioned, no, the PS and DS. PS and DS points are having high, moderate to high coherence levels. But majority of the pixels in the images are noisy, or you can say the coherence level is very low. If coherence level is low, it means those images are not suitable for the, or those pixels are not suitable for the interferometry, or you can say whatever the deformation you are calculating over those pixels, those are not reliable. So it is better to ignore those pixels and only concentrate on the PS and the DS pixels. So those things are basically the InSAR, classical InSAR limitations are mentioned over here. Like InSAR based deformation measurements are related to quality of the signal correlation. Okay, signal correlation can be limited by changing in scatter properties within the temporal decorrelation. If temporal decorrelation is more, the signal is completely noisy. Temporal decorrelation due to dielectrically changes in the scatter property like vegetation, water content, or the other phenomena by which the dielectric properties are going to increase, and hence the backscatter information may be high, but that doesn't mean the deformation over that particular area is high. Okay, so interferometric phase decorrelation has another source due to the geometry of the SAR acquisition known as the difference in incidence angles, and that may be big impact on the large baseline which or spatial baselines. Okay, so an atmospheric delay is another limitation, because the atmospheric corrections we are not able to do very precisely in the InSAR techniques. So these are few limitations. Now coming to the main multi-temporal InSAR techniques. So here you can see the deformation. Generally we are early, or you can say in the traditional way, we were measuring the deformations like terrestrial methods, labeling equipment were using, GPS, high precision GPS devices were used, but these are basically giving the point information. Suppose you are putting GPS somewhere, so it is continuously giving the X, Y and Z and the time of that particular location, and over a period of time what is these coordinates values are changing. So those things you can investigate, and then you can understand, okay, how that particular point over the surface is going up or down or the horizontally in any particular direction. And same thing can be done using the labeling equipment, but keep in mind these are only the point observations, these are not continuous observations. Then photogrammetric techniques are there, laser scanning is there, that is also very costly techniques. You cannot scan a very large area of the earth surface using the laser, and if you are doing this, it is very time consuming and the data volume will be very huge. So you have to analyze, it means high performance computers should be there with you. So this is again very costly techniques. Differential SAR interferometry, which we are going to discuss here, and then microgravity methods. So these are basically the direct methods by which we can understand, okay, how the land surface is going upward direction or the downward direction, because the surface of the earth is directly governed by the gravity of the earth. So where the gravity is large, and what is the role of gravity over the different parts of the globe, and accordingly we can understand, okay, the how the deformation is varying over the earth surface. But these techniques, point techniques, have certain limitations, because the leveling equipments generally we are using in the surveying. So surveying means you are going into the field, collecting the data sets. So the survey itself is a very costly affair, and the frequency of observation is also very limited, and whatever you are observing, that is again a point data sets. So that is not basically solving our purpose. And the surveying you can do over a small area. If you want to analyze, such investigations over the large area, let us say continent wise or global investigations you want to do, it is almost impossible using the labeling equipments or device surveying techniques. So alternative method, or you can say the very precise method, is the differential SAR interferometry. So point is, it can give the continuous observations across the globe, and it can give the data very frequently, means after 10 days or 12 days, whatever the revisit time of the satellite is there, accordingly that much frequent data sets you can receive. But that much frequent data set you cannot receive from the surveying data sets or the laser scanning techniques or photogrammetric techniques. So that much frequency data you cannot observe, okay. And again, those are point data, and our satellite data is continuous in nature. So frequency is very high, in continuous way we are getting the data sets. And then thing is, whatever the output we are expecting from the differential SAR interferometry, the accuracy level of those outputs is almost matching with the terrestrial methods like GPS methods or the labeling methods, because the accuracy of the labeling or the GPS technique is sub-millimeter, or you can say the millimeter scale accuracy is there, and more or less similar level of accuracy we can expect from the INSAR techniques, or you can say the advanced version of the INSAR techniques with the modern advancements, okay. So accuracy wise we are not losing anything. Additionally, we are having continuous data and the more frequent data set, so that the deformation can be monitored regularly. So many advantages are there of the INSAR over the other existing techniques. So here you can see these are the differential SAR techniques. One is classical INSAR technique, second one is interprogram stacking, third one is small baseline subset analysis, and the fourth one is the PSI, persistent scatter interferometry. So PSI and SWOS are called the advanced versions of the INSAR techniques, but these are also called, in fact all of them are called the multi-temporal INSAR techniques, but popularly specifically SWOS and PSI are called the multi-temporal INSAR techniques. Nowadays people are using or started developing some more advanced techniques by combining the strength of the individual multi-temporal INSAR technique like SWOS and the PSI. So you can say that in the current scenario, some hybrid INSAR techniques are also there in the literature. So they are basically combining the role of SWOS and PSI techniques. And you know, every technique has its plus and minus, or advantages and disadvantages. Same way, SWOS has certain advantages, certain disadvantages, and this is advanced technique. Same way, PSI also having certain advantages and disadvantages. So every technique is having advantages and disadvantages. So people have started thinking like, if you are combining these advanced techniques and we are generating some hybrid techniques, and we can combine both the techniques in such a way that whatever the limitations or the disadvantage of one technique is there, so that disadvantage can be overcome by the advantage of the another technique. For example, disadvantage of the SWOS can be overcome by the advantage of the PSI, and the vice versa. So in this way, if we are able to combine, it means the overall performance of that combined or the joint or the hybrid method will be better than the performance of these individual techniques, okay. So just here you can see the SWOS and PSI are advanced multi-temporal techniques, and they are working only on the point data sets, and they are working over the PS and DS pixels. Like in PSI, the name itself suggests persistent scatter interferometry. So they are mostly working with the PS points. It means the PS point, which are where the coherence level is very high. So over those pixels this technique works. And SWAS is a small baseline subset analysis. It means in this technique we are considering the pairs of the interprograms which are governed by the small baselines, not the larger baseline. In PSI the baseline may be larger also, but in SWAS all the baselines will be small. All baseline means temporal baseline is small and the perpendicular baseline is also very small, so that it can basically reduce the decorrelation effect. Or you can say we are keeping in mind that if the baseline is small, so the decorrelation factor will be small and hence the accuracy of measurement will be high. But in PSI we are considering persistent scatter point itself. It means the phase and the coherence is very strong over those PS points, and whatever the outputs are coming, those are highly accurate. Okay, but in classical INSAR only two images we are combining, and then if you are interested in the time series analysis, so such processing we have to repeat again and again, and this technique is also required very accurate DEM, classical INSAR. If you are not having very high resolution DEM, it means the accuracy of measurement of classical INSAR will be poor. But these advanced technique SWAS and PSI, they don't require very high resolution DEM. It means the coarser resolution DEM can also work with the SWAS and PSI techniques, because these techniques themselves calculates the topography. So very highly accurate DEM is not required. And this interprogram stacking technique is just simply temporal summation of the interprogram, and the combined characteristic of all the interprogram is being analyzed. So these are the few techniques, and now let us see. This is the persistent scatter interferometry. So as I mentioned here, this is the PS point. This we have already seen earlier. So here you can see the potential method for the time series analysis. Okay, or you can say the origin or the starting of the PSI, or you can say the birth of this particular technique was happened in the year 2000. So in the 2000 people have developed this. The Ferretti have basically started this particular work, and they have patent in their name also. So this technique is independent from the surrounding incoherent pixels. As I mentioned, the coherent pixel, this technique works on the coherent pixels, not on the incoherent pixels. So suppose in particular area few points are there which are reflecting very strongly, so that the coherence is very high. So this technique is working only on those pixels, and hence since those pixels are very strong, coherence is very high, it means whatever the output you are getting, the accuracy of that output is also very high. Okay, and this technique is not considering the other pixels, or you can say the adjacent pixels which are incoherent in nature, or you can say the noisy pixels. Okay, it works on the selected pixels only, not all pixels in the study region. As I mentioned, in the INSAR techniques, the phase difference is calculated over each and every pixel. That's why most of the pixels may be noisy, or you can say whatever the output you are generating, deformation output you are generating, at most of the pixels the accuracy is bad or not reliable. Okay, so in the advanced technique, people started, instead of considering all the pixels, only work with the selected pixels where the output is very reliable. Okay, so this technique is working only on the PS points, and these points selected the pixels means pixels with the stable phase and the high coherence throughout the investigation period, elevation values with some meter accuracy, and the surface movement with millimeter accuracies can be acquired. So if you see here, this in this particular graph, this side is called, this is temporal baseline, this side, or you can say the acquisition date, and this side perpendicular baseline is shown, and the red dots are representing the image time at which the image was acquired. Then so many red dots are there, you can say so many images are there, and out of them one image is considered as a reference image, that this image is basically the reference image. Then from the reference image, the pairs for with other images is constructed, like pair from between this and this image, this and this image, this and this and this. So each line is basically representing an interprogram, because this line is connected with two images, one image on the one side, another image on the other side. So in each pair two images are there, or that line is basically, now you can understand, the line is governed by the baseline. So suppose if you are talking about this particular line, so one end of this line is here, another end of this line is here. So you can say this line is from here to here, so you can say time is varying from here to here. So you can say July 2020 to July 2021, means temporal gap is almost 1 year. And what is the perpendicular baseline? So perpendicular baseline here is around 70, and here it is around 0. So you can say the perpendicular baseline is around 70 meter, and temporal gap is around 1 year. So this particular pair or interprogram is governed by 1 year temporal gap and 70 meter of the spatial gap. So this way means all the pairs are generated, or suppose 100 images are there, so 99 lines you will get, or you can say 99 interprograms you will have. And this particular graph is called basically star network. And the reference image in the PSI analysis generally comes in the middle. Here you can see the images are varying from here to here, but the reference image is almost in the middle. The reason being, first thing is the coherence should be high. Coherence should be high means sum of coherence, means coherence between this pair plus this pair plus this pair plus this pair plus all the pairs. The sum should be maximum or highest, and that is only possible if the temporal baseline is half. So it means the reference image is almost in the middle, so that this side the coherence will be high, this side the coherence will be high, not at all the images or all the pixels, only at the selected pixels. Okay. So suppose this point, this reference image I am taking, let us say over here. So this network will be like this, line from here to here, 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 so here to here, here to here, and from here to here. So means this way you will have the network, but that will not look like a star network. Okay. So that will be just like a conical structure. So in that case, what will be the maximum temporal baseline? From here to here. So that may be, July 20, this is April 2022. So it may be 20, 21, 22, almost 2 years. It means from here to here the temporal gap will be 2 years. It means there are more chances that the signals will be decorrelated, or you can say coherence level is less. So automatically, the sum of coherence will be down. But the reference image or reference image wants the sum of coherence should be maximum. So that is only possible if you are taking almost in the middle, but you cannot choose as a middle, but you have to do the calculation according to that particular relationship which I have shown in the first slide. Okay. So if you do that analysis using that relationship, then automatically you will get the image or reference image almost in the middle. Okay. So this way we are forming the interprogram and then generating the time series of the phases between the reference and the secondary images, and those phases are converted into deformations. So the time series of the deformation can be achieved. So now first we will come to the advantage of this particular technique. Means what is the advantage? Advantage is, suppose this baseline is from here to here. So this is 2 years time gap of the images. Suppose you are taking 10 years of the data or 20 years of the data, and then again if suppose 10 years data is there, then you are taking this reference image in the middle. So either side 5 years gap will be there. And if you are applying this technique and you are getting some points, it means those points are PS points. and it means after 5 years of the gap you are getting the PS points. It means that target is not changing very much, and hence the accuracy and if the point is not changing very much, it means whatever the phase difference you are going to calculate, and hence whatever you are converting that phase difference into path difference, so that path difference, or you can say the deformation, will be very very accurate. So you can say the accuracy of such measurements will be very very high, or millimeter scale accuracy you will achieve. Okay. And drawback of this technique is, suppose you are by this much large baseline, means 10 years data you have taken, so either side 5 years data gap is there. So suppose some region is so dynamic where the features are changing very rapidly, and hence the signals are becoming completely decorrelated, because 5 years time is not very less time. So point is, if within 5 years, suppose you are working in the forest region, so for in 5 years the canopy structures of the entire forest will be different. If it is changing, it means the signals between the first image or after 5 years, they will be completely decorrelated. It means that pair is not suitable for the interferometry. So point is, if you are choosing a study area of this type or the natural environment, then you will not get any of the PS point is that you will not get any point. Means we were expecting some points, because this techniques works on the persistent scatterers, but if this types of the study area is there, no PS you will get. If no PS you are getting, it means this technique is failing, this will not work, or you can say this technique fails over the natural environment, because there the targets are changing very rapidly. So for the longer period, if you want to apply the PSI technique over the natural environment, then it is very rare that you will get some points, you will not get the points. Okay. But yes, if this technique, if you are applying over the urban area, or you can say where the buildings are there, so those buildings are not changing very frequently, so this techniques can work over the urban areas for the longer period also. So point is that this technique is applicable or gives the accurate information, but over the man-made structures, or you can say the urban areas, but for the natural environment and for the longer period it will not work, because sufficient PS points you will not get. Then what you can do, you can basically relax the criteria, like coherence criteria you can relax. Then instead of considering only PS, because PS are not available, then you can give the some less threshold value over the coherence. Then the moderate coherence points you can also invite, but if you are invite, it means DS points you are inviting, then you can do some analysis. But this is again up to a certain extent, you cannot relax your coherence criteria so much. So much means you cannot consider the points below 0.4 or something like that. If you are considering below 0.4, 0.3, it means the outputs are not reliable. So keep in mind, this techniques gives very accurate results, very highly accurate results, but PS should be there. If natural environment is there, it means PS will not be available. It means this cannot work for longer time series. Second thing is, since the accuracy of measurement of this technique is very high, it means these techniques are applicable over very very slow deformation. It will not give the correct results over the rapid or the large scale or the high deformation rates, or over the areas where the deformation rate is very high, means the deformation is happening very rapidly up and down. So over those regions it will not give the correct answers. Or you can say the this can fail over the areas where the deformation is not linear in scale, means there are deformations which are continuously, just like subsidence continuously going down slowly, then continuously it is coming up slowly. If such phenomena are there, then it can monitor. But if the deformation is non-linear in nature. Suppose suddenly it is going, then stopped, then for longer time it is stopped, then again changing, and over a large area it is changing, in a different rates. That is basically called the non-linear deformation. So if non-linear linearity is there in the deformation phenomena, then in that case this again this techniques cannot work. So keep in mind where it can work and where it cannot work, and wherever it is working it can promise very high accurate results. So the level of accuracy basically is very good thing for this particular technique. So here you can see the PS and DS points, like in all the images, let us say this particular image, this particular dot is representing PS. So if you draw this graph, here you can see the phase is changing very rapidly, and this is also continuously increasing. And choosing the PS candidate, PSR is smaller than a resolution cell. Actually there is a difference between the resolution cell and the PS points. Generally we are considering the pixel as a PS point. So the PS should ideally have the constant velocity over series of SAR images. If it is not constant, it means non-linearity is there, it means these techniques may fail. PS candidate selection algorithm works best if starting with relative short baseline and working up to include the large baselines of the SAR images. Now another technique is the small baseline subset analysis. This completely work on the DS or the distributed scatterers. So here you can see here all the pairs of the interferograms are governed by the small baselines, both temporal as well as the perpendicular. So here you can say this side is the time and this side is the perpendicular baseline, temporal baseline, perpendicular baseline. So instead of considering a single reference and then making pairs, here it is mentioned like you make the pairs between the images, red dots are representing the images. So connect the images from, let us say, from here to here, then here to here. It means this line is representing one interferogram pair. So this pair is governed by a small perpendicular baseline and a small temporal baseline. So here you can see over each pair, let us say this pair, a small perpendicular baseline, a small temporal baseline. So it is not like that reference image was considered here and from here to here the pair was connected, and from here to here another pair, from here to here another pair, just like in the PSI technique. So there you are getting the large baselines, but here all baselines are small in nature. So what happens, there will be high level of coherence or high level of similarity between both the images of the corresponding pair. Suppose if you are talking about a particular line, let us say this one, it means this image and this image, these signals are highly correlated. So in order to make the high correlation between the signals, such types of the configuration was opted. So what happens, suppose 100 images are there, then they have formed the interferogram pairs with small lines. So how many interferograms can be generated from 100 images, or let us say n images are there, then how many pairs can be generated? Like from n images, pair of 2 can be. So the number of interferogram will be nc2 and combination of 2, from out of n combination of 2. So nc2 pairs will be there. So nc2 equal to factorial n divided by factorial 2 factorial n minus 2. So it will be n minus 1 and factorial n minus 2, that will be cancelled out. So it will be n factorial 2 is 2. So it will be n minus 1 divided by 2. Point is that if n images are there, then total number of interferograms will be n minus 1 divided by 2. But in case of PSI, if n images were there, then how many interferograms were there? Suppose n was there, 100 images were there, so 99 interferogram. It means n images are there, so n minus 1 interferograms were there in case of PSI. But here the total number of interferograms will be n into n minus 1 divided by 2. So suppose if you taking the examples of 100 images, so there in case of PSI total number of interferograms were n minus 1, that is 99, and here it will be 100 into 99 divided by 2. So 99 into 50, so it will be 4950. You just think, suppose you have 100 images. In case of PSI you are having 99 interprograms, and here you will have total 4950 interprograms. And see, each interprogram has its own size. Though the input images are same, 100 images are there, 100 images are here, but there you are having only 99 interprograms. Here you are having around 5000 interprograms. So the size of interprograms will be more here. If more size, if suppose more size is there, it means it is difficult to process into the computer system. It is easy to handle 99 interprograms instead of 5000 interprograms. So data handling capacity is more here. Plus point is, all the points or all the baselines are small, that's why the signals are correlated, highly coherent, and hence you will get sufficient points of measurement and you can get the better outputs. But drawback is more number of interprograms are there, so it becomes very difficult to handle them. So again thing is, relaxation is, it is not necessary you should generate all 4950 interprograms if 100 images are there. It is not necessary, because out of 4950 interprograms, most of the interprograms are having similar information, or you can say the redundant interprograms you will have, just like in case of the hyperspectral remote sensing. Most of the bands are having the similar information. So same situation is happening here, means out of 5000 interprograms, or almost 5000 interprograms, most of the interprograms are having similar information. So it is suggested that you should not consider the interprograms having the similar information. So suppose 45 interprograms having similar information, so use only one interprogram out of 45. So by using this particular concept, you can reduce the number of pairs from 4950 to let us say less than 1000, or in those numbers in which you are comfortable to process, or your computer is capable to process that. Okay, so people are not processing NC2 interprograms, they are processing much less than NC2 interprograms. So let us say out of 5000 we are processing only 500 600 interprograms, so others we are ignoring. Okay, just like this is also example of ignoring so many interprograms, only few interprograms are shown in this particular graph. So what you can do, you can ignore most of them, you can select only few interprograms where you are comfortable, but you cannot reduce this number of interprogram less than the interprogram which you are generating in the PSI. You cannot say here in SWOS total 4950 interprograms are possible, but you are generating only 50. That is not good. Good in the sense, in PSI you are generating 99 interprograms, so you should not go below 99 if 100 images are there. It means whatever the interprograms you are choosing in the SWOS, these number of interprograms should be greater than or larger than the interprogram of the PSI technique for the given set of images, but it may be less than the total possible interprogram, that is NC2. Okay, so that way the accuracy or the of this particular technique is going up. But here you can see these are the NC2 interprograms, the given images are there. So you see, if you are generating NC2 interprograms, so these number of interprograms you have to generate. So these are large number of interprograms. So point is, you should not generate these number of interprograms, because most of them are redundant or most of them are having the similar information. So in that case you should go with this particular type of the configuration. Okay, so I hope you understand. So this technique is also advanced and giving and this techniques can work, because the limitation of the PSI was that can work over the urban area very precisely, but that fails over the natural environment, especially in the forest region or the hilly terrains. But the SWOS can work there. because its baselines are small. So by reducing the baselines, the correlation is enhanced, and hence the some pixels can be picked over the natural environment also. So you can say this particular techniques works well over the urban area as well as the over the natural environment. So this is the advantage of this particular technique. Okay. So these are things we have already mentioned. Now people are contributing small things over the basic SWAS techniques, and they are also giving different names of the SWAS technique like CPTA, NSWAS, STWAS, MSWAS, like these. So these are basically I picked from some paper. So the references are mentioned below. So these things basically you can just, but basic funda is same in the SWAS, but small contribution they have added, and they have changed the name of the technique. Okay. So you can say from 2002, or you can say the birth of SWAS technique was happened in 2002, or you can say slightly later than the PSI technique. So from 2002 to 2019, the progress is mentioned in this particular slide. So now people are developing the merge technique or the joint techniques or the hybrid techniques also, just by combining the potentials of individual techniques, and in place of the drawbacks of the other technique. So here you can see the time series analysis from PS method and then DS method, and finally they have combined or the merge. So the merge techniques can also be developed. So here whatever the limitations are there with the SWAS, those are just opposite of the advantages or the disadvantages of the PS techniques. So both if you are combining, then the overall accuracy of the merge or the combined techniques or hybrid techniques can be improved. So here this is basically showing the number of pixel points or scatter plot or histogram of these points. So here you can see this is the distribution of the PS points, which is less in number, and this is the distribution of the SWAT technique. More number of points we are getting in the SWAT techniques. If you are combining both of them, then more number of points you can get in the merge techniques. So this way the density of measurements points can be enhanced by combining the outputs of the PS and the SWAT techniques. In fact, directly outputs are not combined. The initially some steps are performed over the PSI and some steps are performed over the SWAS. After those basic steps, the outputs is combined and the other processing chain is performed by combining both the outputs or middle of the outputs, so that the overall performance of the joint processing can be enhanced. These are the techniques for the PS selection. First, I have already mentioned the amplitude dispersion technique. So here you can see this is the pixel phase, this is the acquisition date. So this this blue crosses, this type of the distribution you are getting, it means this shows the PS points, and these red dots, which basically some deviation is there or amplitude dispersion is there. So these points are basically considered as a DS point or distributed scatterers. Okay. So you can say if the phase response is almost constant in all the images, all the pixels, so those pixels are called throughout the investigations, basically that is called the PS point. If it is changing, it means that is DS, and if this scatter plot is very zigzag or no uniformity is there, it means those pixels are noisy. So from the distribution of phase versus acquisition time itself, you can identify which pixel is PS and which pixel is DS and which pixel is noisy. And this is another technique called the signal to clutter ratio, which is the standard deviation is phase standard deviation is calculated from this relationship. So this RSC is basically A square upon C square, where A is amplitude and C is the clutter radius. So using this one, phase standard deviation variance can be calculated, and based on this some threshold value, the pixels can be picked up, and those pixels are PS or per second scatterers. This is phase stability. Based on the phase stability itself, you can identify the pixels, and this is another correlation based analysis, or you can say the coherence based. This is also very simple. You can just put a threshold over the coherence values, let us say coherence value threshold you are putting more than 0.8, it means those are highly correlated point, or you can say PS points. Okay, so this is ends with this lecture. So now if you have any question we can discuss. So no gap was given in the at the end of the first lecture, so both the things we can take together. So if you have any questions, let us discuss the questions if you have.